Hello, doctor. We are from group 2. Today we're going to present experiment 3, which is vapor compression refrigeration. Introduction for this experiment is heat naturally flows from high to low temperature regions. To research this process, devices like refrigerators are used. Refrigerators are cyclic systems that use a working fluid called a refrigerant to transfer heat from a low temperature area to a high temperature one. Heat pumps work similarly but with a different goal. While refrigerators aim to keep spaces cool by removing heat, heat pumps are designed to heat spaces by transferring heat from a cold source to a warm area. Refrigeration is widely used in both industrial and domestic settings for preserving food and chemicals. It removes heat from low temperature areas and can also function as a heat pump to warm spaces. Objective of this experiment is to determine the coefficient of performance, which is COP, for vapor compression cooling system. Scope for this experiment is the flow rate of the water to the evaporator was fixed at 25 grams per second. Water was used as the cooling medium in the condenser and the evaporator section, the vapor compression refrigeration system, and finally, changing the flow rate the water to the condenser between 35 to 40 grams per second. For the theory part, the vapor compression refrigeration system is widely used thermodynamic cycle that transfer heat from a low temperature area such as a refrigerator or evaporator chamber to a high temperature environment like ambient air or cooling water by performing external work. This process relies on the second law of thermodynamics, which states that heat cannot spontaneously move from a colder body to a hotter one without external energy. Therefore, a compressor is used to do work on the refrigerant to make this reverse heat flow possible. The system operates in a closed loop and consists of four main components: the evaporator, compressor, condenser, and expansion valve. In the evaporator, the refrigerant absorbs heat and evaporates at low pressure. The low pressure vapor is then compressed to increase its pressure and temperature. In the condenser, it releases heat and condenses into a liquid. The high pressure liquid passes through the expansion valve, reducing its pressure and re-enters the evaporator to continue the cycle. The performance of the refrigeration system is measured by the coefficient of performance, COP, defined as the ratio of the heat absorbed in the evaporator, which is QL, to the work input to the compressor, which is work. We can find the COP for refrigerator using this formula QL over W.
Next is the experimental setup. For this experiment, we use refrigeration cycle demonstration unit R63 PE10 which using R141B refrigerant fluid. There are 11 components we need to identify for the experiment, which is the condenser water flow meter, condenser pressure, watt meter, condenser, valve, main switch, evaporator water flow meter, evaporator pressure, evaporator, compressor and also thermometer. Next, we move on to the methodology of the experiment. Firstly, we need to identify each component as stated in the experimental setup, which I mentioned just now. There are 11 components to be identified. Then, open the valve. Secondly, open the water pipe and set the water flow rate to the evaporator as 25 gram per second and water flow rate to condenser as maximum. Throughout the experiment, our group need to make sure the water flow rate to evaporator is maintained at 25 gram per second, and at the first round of the experiment, we set the water flow rate to condenser as maximum, which is 50 gram per second. Next, switch on the main switch and allow the cooling system to be stable approximately 10 minutes and record the parameters as listed in the table result. Next, we repeat the experiment by changing the flow rate of water to condenser in between 35 to 40 grams per second, then repeat the experiment for 4 times. From our experiment, our group repeat the experiment by changing the value of flow rate of water to condenser from 40, 38, 37 and 36 grams per second. Lastly, when the experiment is done, we follow the procedure to close the device. We switch off the main switch and turn off the water supply pipes after 1 minute, then followed by closing the valve to the shutdown position. The reason to keep water running for a minute is due to the residual heat removal. Because by keeping the water running allows the system to cool down gradually, which prevent the thermal stress and the end to protect the component.
Okay, so these are the results that we obtained from our experiment. So as we can see, the rate of heat transfer at the evaporator as we continue further down the experiments decreases, while the rate of heat transfer at the condenser increases, but just by the slightest. And we can also see that the coefficient of performance is at its peak at 5 in during test 1, and then it reached a constant in test 4 and 5 at the value of 1.67.
Based on the results that we have discovered from this experiment, we have our first discussion, which is to calculate the rate of heat transfer that occurs in the evaporator and the condenser for the 5 test runs. The rate of heat transfer in evaporation can be calculated by using the mass flow rate multiplied by Cp times T7 minus T1. And the rate of heat transfer in the condenser will be heat of evaporator plus compressor power. And the table below shows the rate of heat transfer of evaporator and rate of heat transfer at condenser from test 1 to test 5. So from the table, we can know that the rate of heat transfer of evaporator gradually decreases. A decreasing rate of heat transfer of evaporator suggests that the system is absorbing less heat from the evaporator side, indicating a reduced cooling performance or capacity. The condenser rate of heat transfer stables from test 2 onwards to test 5, with a slight spike on test 1. Sharp drop after test 1 suggests a significant reduction in heat rejection, likely due to reduced heat absorption or lower refrigerant mass or a reduced mass flow rate. Consistent Q2 values from test 2 to test 5 implies that the system may have reached a stabilized operating condition after the first test.
So in discussion 2, we will explain the effect of changing the condenser flow rate for T1 to T6 to the compressor power. So this is a graph of temperature T1 to T6 against the SLU condenser, where the y-axis is temperature and x-axis is SLU condenser. From the graph, you can get the observation that from T1 to T4, it show a minimum change only, indicating the stable internal temperature under changing flow rates. When it comes to T5, it suddenly rises sharply as condenser flow rate decrease. This indicates the heat build-up and the potential of overheating risk. And come to T6, it backs to relative stable, but at the last part, it shows slightly warming at the lower condenser rate. Next, we'll discuss about the relation between compressor power input and the SLU condenser. Here's a graph of the compressor power input against the SLU condenser, where the y-axis is compressor power input and x-axis is SLU condenser. From the graph overall, we can say that the SLU condenser increase, the compressor power input also increase. This is because the water acts as a heat exchanger in the cycle. As the water flow rate to the inlet of the compressor increase, It will also increase the amount of the refrigerant in vapor state available the inlet of the compressor, thus increase the compressor input power.
Okay, so in conclusion, the vapor compression refrigeration experiment demonstrated how system performs varies with changes in operating conditions. The highest COP, coefficient of performance, of 5 was observed in test 1, where the system had the highest heat transfer at the evaporator and relatively low compressor power input. This indicates the efficient operation under those initial conditions. As the test progressed, the COP decreased significantly, stabilizing around 1.67 in test 4 and 5. This drop in performance corresponds to lower heat transfer rates at the evaporator and changes in both evaporator and condenser pressures. The variations affected the refrigerant flow and overall cooling capacity of the system. The negative heat transfer values at the condenser in later tests suggest that there might be possible experimental errors or system inefficiencies. Overall, the experiment highlighted the importance of maintaining optimal pressure differences and operating parameters to achieve high efficiency in vapor compression refrigerator systems.
Lastly is the safety procedure of the experiment. Firstly, ensure the lab is well ventilated to avoid the inhalation of refrigerant gases, and make sure the temperature of the refrigerant is normal. If the refrigerant is too hot, it may not condense properly in the condenser, and this will lead to incomplete phase change, which throw off the entire refrigeration cycle and affect system performance. Secondly is the operational safety. We need to always monitor pressure and temperature readings throughout the experiment. Also, to ensure the system is internally stable, as stated in the methodology of the experiment, we need to allow the cooling system to be stable approximately 10 minutes to avoid the fluctuation data and system stress. Lastly is handling water flow system. Ensure the water pipe are securely connected to prevent spills or leaks that may cause leaks. And this is the list of references that our group used. And that's the end of the presentation from our group. Thank you.